Hey everyone, Benjamin here from the Zephyr project. Beginning of March 2025, Friday, March the 7th, and a new release of Zephyr is out, Zephyr 4.1. As always, I'm going to take a few moments, hopefully not be too long, but walk you through some of the new and noteworthy of this release. As always, there's a lot that went into this release. In fact, I think we had a record number of contributors, close to 700 individuals who effectively contributed code one way or the other to this particular release. So yeah, a lot happened in the past 4 months. It's kind of always a challenge to highlight and put the spotlight on only a few of the many things that that made it into the release. But yeah, let's jump right into the release notes and the highlights. As you can see here, I can probably working draft at the time of recording, but when you will be watching this video, those will be the final release notes, starting with performance improvements. We're going to talk a bit about what that means. Support for IAR compiler for ARM, basically opening the door to giving access to this commercial compiler for folks interested in getting potentially better performance, more safety features, certified compilers, basically. Support for REST, writing REST applications, REST code on top of Zephyr. The USB MIDI class driver, this one is really fun, I guess I should say, like literally, that's among other things, it is fun. It means that you can actually build music instruments using Zephyr and using the USB device support in Zephyr. So stay tuned for the demo part for that one. Lots of new boards. I think it's a record as well. I mean, I'm not so much after like vanity metrics and whatnot, but getting 70 new boards in just one release cycle is actually really impressive. And there are some boards that I think you would be interested in hearing that they effectively landed in Zephyr, and then a few other things that I will try and demo. As always, I want to use this as an opportunity, as an excuse to give you some tips and tricks of things like new tools, new shell commands and whatnot that may have appeared in this release, and that will be like, when you hear about them, you will be like, oh yeah, I wish this had existed before, and I wish I knew it was there. Well, guess what? It's there now, and you will hear about it. So yeah, how about we start with the performance improvements? It's actually an effort that started well before the 4.1 release cycle and merge window opened. This basically work on making sure that the Zephyr kernel was as performant as can be. And one thing that I like to say and remind people, and actually I think we sort of see that kind of on the left-hand side here, Zephyr RTOS, yes, it is a kernel, and I think, I mean, we can see that here, right? It is a kernel. It is what's going to support your, you're going to write code that requires multiple tasks, that requires synchronization, that has real-time constraints. So of course, you kind of want a kernel to support those use cases. But Zephyr is much more than that, right? It's an entire development stack with connectivity, like network connectivity, be it Wi-Fi, Bluetooth, and whatnot. Lots of pre-integrated subsystem libraries, modules, sensor drivers, you name it. And in a way, the RTOS is only a small part of that, but it's a critical part. Like you want the real-time kernel to add as minimal of an overhead as possible to your actual application, right? To your actual payload, if you will. So with that, let's jump actually to some benchmarks, just to show you kind of the work that went into improving Zephyr. Looking at the kernel, looking at the benchmark, which I will say a few more words about in a few minutes. But basically, that benchmark covers and allows to evaluate and compare potentially real-time operating systems for a category of things that you typically expect from an RTOS. allocating memory from memory slabs and like having memory managed by the RTOS. So what kind of throughput you can expect there? What's the throughput you can expect from doing message passing from one thread to the other, synchronizing threads? What's the overhead of using things like semaphores and whatnot? How many times per time unit, if you will, you can switch from one thread to the other using a preemptive scheduler, using a cooperative scheduler, those kind of things. So pretty abstract in a way, but like it's the benchmark is really well structured and well established also, and allows to really compare things. Those sort of raw performance numbers. They are only raw performance numbers. I will be saying a few more words about that, but it's useful, right, to have this kind of reference point. So Zephyr 3.7, which you see in light purple bars on the chart, has been set as the reference, basically. So 100% or 1 would be the performance of Zephyr 3.7 in terms of respectively memory allocation, message processing, etc., etc. And you can see that in dark purple, Zephyr 4.1, there's a significant boost, right? Like there's quite a lot of work that went into using actually that benchmark as a guide or as a help to spot some performance bottlenecks. We've drastically improved actually, and sometimes it was a matter of just tweaking existing configuration options, and sometimes it was just like plain optimizations that we're just waiting to be done in the kernel, and a lot of the work that's been done actually benefit all the architectures and ARM in particular. Actually, there's also some like specific improvements that have been made for ARM, ARM Cortex M. So yeah, that's so for that chart. Before moving on to the next one, something else that's interesting to see and kind of a reminder of how modular, flexible, configurable Zephyr is. At any point in time, you can tweak how you want your final sort of Zephyr-based binary to be like, right? And kernel-wise, you can decide which scheduler you want to adopt. And if your use case requires you know that you will be relying more on cooperative scheduling than you will be on preemptive scheduling. There might be scheduling algorithms better suited for that, namely the multi-queue, ready queue algorithm or policy is kind of an interesting one, and you can see that it gives a serious boost compared to the only 20% boost that we got otherwise in 3.7. In 4.1, sorry. So yeah, multi-queue, you just enable that with the kconfig option. It will probably have some impact on your RAM consumption and the size of your binary, but it might be what you need, right? And it might also have an impact on preemptive scheduling. So it really depends on the use case, right? And that's actually one thing that I want to stress before jumping to the other aspect of the other thing that I wanted to show you is that until performance is really a key concern for you when it comes to selecting an RTOS and or selecting a particular hardware target that's going to be your main, the target for your application, I would really recommend people don't think too much about performance and raw metrics, if you will, with regards to their real-time operating systems, because there are many use cases where it's really only going to be just one of the many things you want to look at when you select the RTOS. Like it's also going to be about what's the breadth of the ecosystem around the RTOS, how many libraries and third-party toolchains, compilers, IDEs are already sort of compatible / integrated with your this particular RTOS. What's the open source community like for the if you care about an open source RTOS, you probably are interested in more than just the code. You care about the community. You care about the way the project handles and deals with security vulnerabilities, things like that, right? And so all that to say that performance is important, and even more so for some use cases, but it's only one aspect. So with regards to comparing the performance of Zephyr compared to other RTOSes, following the improvements that have been implemented and the performance improvements in the Zephyr 4.1 kernel, it's actually interesting to see that, and as opposed to benchmarks that were actually made available, I think late last year, late in 2024, you can see that compared to, say, ThreadX, for example, Zephyr is pretty much on par, right? Like, I mean, depending on what you look at, it's either 10 or 20% percentage points behind ThreadX, or 30, or sometimes it's ahead, right? And that's so I hope that sort of like blurs the line even more of, yes, performance is important, but it's not to the point where Zephyr or whatever else RTOS basically is just so fast and or so slow that it's either going to be a no-brainer or something that you would totally avoid. So yeah, like I think it's interesting, and also interesting to see again that if you play with the options and sort of like you fine tune the compilation flags for your kernels, you can significantly influence the results. And it's true. I mean, I've done that for something that I know a bit, which is Zephyr. Playing with the multi-queue scheduling algorithms, like I mentioned, gives a significant performance boost. Like when you would have thought that maybe cooperative scheduling was slightly behind the likes of ThreadX and FreeRTOS, switching to a different policy just gets you back on track. And I'm sure the same, to be clear, the same probably applies to ThreadX, FreeRTOS, or any other RTOS. Those numbers you may see on benchmarks are always to be taken with a grain of salt. But yeah, that's the work that went into improving the performance of Zephyr. So no matter what, it's going to benefit everyone, right, in their use cases. Something that goes along that and together with this work is this right here, the fact that those metrics, those numbers that I was just showing you, effectively come from the so-called thread metric benchmark. I think originally it comes from way back from like the Express Logic ThreadX days, and that's like a benchmark that was put together by this team at the time. It's now effectively open source. It's now something that is becoming increasingly popular to compare RTOS performances or RTOS's performance. And the what's interesting is that, in switching briefly to my VS Code environment right here, it is available effectively in the Zephyr tree, right? Like in the tests/benchmarks folder of your Zephyr source tree, you'll now find the thread metric test suite pre-integrated and pre-packaged already as a Zephyr application, which and you can actually really easily sort of witness what are the very minimal set of flags that were applied to sort of like put the Zephyr kernel in a mode where it's sort of like reasonably optimized for performance, because after all, you're looking at evaluating the what's the most that you can get out of the kernel. But yeah, you can really easily see what's been applied here, and maybe more importantly, to some extent, because that makes lives of people running the benchmark much easier, is the integration with Twister. Twister being our testing framework, which here what we basically are looking at is the configuration file that indicates, oh yeah, I mean, this project, it contains a handful of test suites or test cases, and this is basically what helps you build and run the tests on actual hardware and capture the output, so that you can fully automate it, just like I'm going to do right now. The board basically that I used to run all those tests that I was showing you is effectively an ST microelectronic Nucleo board that, if I look, so let me see. Let me just catch it in my history. Yeah, right here. I can tell Twister, hey Twister, in my tests, benchmarks, thread metric folder, I think I have a bunch of test suites and test cases. Can you please run them, compile them first, compile them for this particular target, and actually run them. And for that, something that I won't like demonstrate in details, but something to really keep in mind is that Twister, you often see Twister as a Zephyr contributor. You usually interact with Twister as this sort of like system that tells you whether your pull request passes continuous integration or doesn't, in terms of, yeah, it builds or it doesn't build, it compiles or it doesn't. So it can help like run build tests, but it can also perform runtime tests. In particular, when you provide the device testing flags, and when you provide a bunch of like metadata to indicate, hey, on my test machine, on my host test machine, I have a bunch of actual devices connected through various USB or J-Link or whatever interfaces. Then when effectively Twister starts running tests, and when it stumbles upon targets that it actually knows how to deploy code to and connect to serial terminals and whatnot, it does. Which, long story short, is exactly what's happening here. Running the test suite, and I won't go through the whole thing, but effectively what just happened or is happening is that Twister picked up the various test cases defined in the thread metric suite, and it's compiling them. And as soon as it will be done, I don't know like which one will be first, but whenever one of those will be ready, compiled, binaries ready, yeah, there we go. So that's cooperative. Apparently, cooperative has now been effectively, like, the test has been run. And what does that mean, among other things, is that we've actually captured the output of the test. And so those numbers that I used to create the benchmark, the charts you saw earlier, you can obtain them really, really easily with like whatever is your target of choice. And here, like, obviously this is a Cortex-M board, but you may want to run similar tests on, you may want to compare Extensa performance for ThreadX versus FreeRTOS versus NetX versus Zephyr versus X. And at least for the Zephyr part, you now have like a really, really easy, super easy to script, also like a fully automate way of running the benchmarks. So yeah, that's what I wanted to show you first. So yeah, please have a look and run your own benchmarks also, like, and maybe more importantly, rather than benchmark, like run like tests that actually correspond to what is your use case, right? You might rely more on some aspects of the kernel and or Zephyr in general. So make sure that you actually test that. Don't necessarily put too much thought or too much importance to just like raw performance metric numbers. So yeah, that was for the long-ish part on the performance improvements, but that's actually pretty very, very great work that went into the release. And I'm not even sure this is finished. I think there's still a few pull requests in flight and still some ideas on how to improve things even further. Along-ish the same lines of performance, speed, the IAR commercial compiler. So yes, full disclaimer, you probably know that already, but this is a commercial compiler. You will need a license to use IAR with Zephyr, but the folks at IAR recently joined the Zephyr project as a member company. And what I personally like even more is that they joined also as like actual contributors. They started contributing upstream some code namely making it possible to use their toolchain for building ARM applications. Quick demo coming up, but one thing worth stressing is that it's really, I mean, every release cycle in Zephyr is only 4 months, so in many ways it's short, right? And so like the support for IAR landed in this time frame. It's a first, see it as a first iteration, right? It might still have some rough edges, but it does work. And as you will see just now in the demo, it's already it allows to demonstrate a few interesting things, in my opinion, at least. Which is so let's see. Yeah, basically let's look quickly first at the documentation. Sorry for the back and forth. Setting up using a sort of third-party toolchain in Zephyr, or at least using a toolchain that's not the Zephyr, the ones that come with the Zephyr SDK, like potentially LLVM or the GNU, the stock like vanilla GNU ARM embedded toolchain. Is actually, it's really easy to do. Like, and usually you just set the Zephyr toolchain variant environment variable to whatever toolchain it is you want to use. Could be LLVM. In our case, that would be IAR, because that's exactly what we want to use. And granted that you have a license token, again, reminder, full disclaimer, this is commercial compiler. You will need a license. You need to install the toolchain on your system. And that's it, really. And you don't have to even know what are the specificities of this toolchain in terms of how do I tell the compiler to optimize for size? How do I tell the compiler to do, I don't know, like link time optimization, whatever? There might be some flags that are probably look very different than the GCC flags you might be used to. But it doesn't matter because it's all packaged, and the Zephyr build system is abstracting it all out. So that's pretty neat. So let's see. I want to set the toolchain to IAR. Or first, well, yeah, whatever. Let me actually set it back to Zephyr first. And I'm going to build a hello world for the QEMU Cortex M0 target. Build and run that particular hello world. So right now, since I set the toolchain variant to Zephyr, I'm effectively using the Zephyr toolchain variant and compiles, no warnings whatsoever, and runs. Now switching to IAR and doing a pristine build on the same Hello World sample application. Let's observe a couple of things. One, here, the toolchain being picked up is definitely IAR. And second, there are way more warnings, and many of them are probably legit, right? Like it's basically one of the things that IAR, like other third-party compilers do, like Clang would do the same. Sometimes they're smarter than GCC, or sometimes they just happen to have like different default warning settings. But in this case, it's probably spotting a few, I would say, code smells, right? Either in the Zephyr code base or in some drivers, some HALs. And where I'm getting at basically is that I actually pretty excited that IAR is now available, because that means that more people will be starting to compile Zephyr using slightly different like compilers, slightly different settings than what we typically do. And we will start spotting potentially some, if not bugs or if not like fundamental issues, at least things that could be like structured, designed better, so that to minimize dead code and like things like that. And this is really important, of course, in like a safety certification kind of context, but not only, right? And it kind of complements nicely the tools that we already have and already use extensively on the Zephyr code base, things like Coverity to do code analysis and spot those exact kind of issues. But I wouldn't be surprised if IAR catches some that Coverity doesn't, and probably the other way around. But long story short, compilation happened and code runs. I mean, what else would you expect? So that's pretty nice. And like I mentioned, for you as a user, you don't really have to worry much about how IAR needs to be how you're supposed to call the command line for the various, like for compiling, for linking, etc. It's all abstracted out. And if you want to optimize, say, for speed as opposed to optimizing for size, because by the way, by default, Zephyr would be optimizing for size, which might be a reason why performance might not be top-notch out of the box. But should you want to optimize for speed, just check the kconfig, like set the kconfig, and the build system and the IAR integration in the build system will figure it out, right? And we'll know what that means in IAR terms to apply that compilation options. And there's a few more things that you can tweak through kconfigs. Things like, for example, rather than using the minimal libc, using IARs, which I guess, I'm not an expert, but I guess is probably more efficient, either smaller or faster or both. If your code relies heavily on some C library functions, right? So that's IAR support. Moving on, support for REST on Zephyr. REST is certainly very popular in the embedded world. I'm no expert myself, but I know you know that it helps with writing code that's more secure, basically, and it has a lot more type safety, so that your code is sort of de facto secure, and like your memory is way better managed and things like that. So REST support in Zephyr, full disclaimer, as of today, and probably not in the foreseeable future either, we're not talking about writing Zephyr itself in REST, right? It's really just providing a way, just like we have a C++, like a way to allow people to write their apps, if you will, in C++. The same applies to REST, and enabling REST support is pretty easy. If you don't have a REST environment set up locally, REST up is sort of the keyword you're looking for to help you install a REST compiler and REST toolchains you will need for whatever target you require. And then Zephyr-wise, you need to enable an optional module, right? And like get that module into your workspace, similar to TensorFlow Lite, CMSIS DSP, Thrift, like Apache Thrift, and probably a few others. This is a module that is like one flag away, or like one option away to be pulled into your workspace. It's not by default, but just enable it and then update, like West update your workspace. It'll fetch the module, and said module basically via the config Rust option, similar to config CPP, which you may have used in the past. You if you enable the module through this option, basically Rust supports kicks in, including the integration with the build system, and you have lots of samples available. I mean, not lots, but there's already a few samples available, plus instructions on how you would go about creating your new REST-based application from scratch. But yeah, essentially. So this is my Zephyr like base directory, and so if I look, I've already gone ahead and pulled the module. So if I look in modules, lang, REST, this is where basically all the REST integration comes from, including the samples, right? A few interesting samples. So should I run Blinky? Should I run a Hello World? Yeah, let's go for Hello World, but then I might actually show you the code for Blinky. So building this is really just like building any other Zephyr application. Probably have that somewhere in my history. Yep. So from wherever in my workspace, just ask West to build the Hello World sample. I would need to ask the REST expert. I find it quite slow, frankly, the compilation process. I'm not sure why that is. I'm not sure if it's a REST compiler thing. It kind of feels awkward, to be honest, that compiling something as simple as a Hello World takes, I don't know, like 15 seconds or so. But that's the way it is, and I needed something to tell you while it was compiling. So I'm probably digressing here. Let's see, we have binary being linked. And so we have something that's ready to be run. Let me just make some room. West build. And we are running in QEMU again, and we are running booting Zephyr. But then when the hello world starts logging, you can tell that it's effectively the hello world that's running. Like I mentioned, showing briefly maybe the code, the Blinky. I wanted to show the Blinky. So the code for Blinky lives in SRC. And yeah, let's see. So this is REST code, right? But then it actually does tap into some Zephyr interfaces or Zephyr wrappers, either to interact with loggers or to interact with devices. Like one of the things you typically do in a Zephyr application is you get typically through C macros, you get handles to device instances, and you start interacting with them using device APIs, hoping that you won't be doing something wrong and trying to interact with a device which is not what you think it is. REST there helps you, right, by making sure that when you use device tree to get a reference to, say, an LED, then effectively you get and you're going to manipulate something that is effectively like the GPIO behind the LED. It is a GPIO in terms of like the typing, and so the only thing you're ever going to be able to do on LED 0, as far as I understand, and as far as you can check also in the code and in the documentation, which I will show in a minute. That's what's happening, right? And it's pretty neat, and it's really only the beginning, of course. So check out Discord among other places. This is where a lot of the Zephyr Restassians engage and discuss, and it's pretty cool, really, to see that. And it's really only the beginning. I mentioned documentation. Let me check it out here. Like the REST doc is generated for those wrappers that I was just describing, like the device tree sort of helpers that help you navigate your different the device tree and some of the existing wrappers around the logging API, some of the raw kernel primitives and things like that. We are planning to have a tech talk on that topic in the near future, so stay tuned for that. But yeah, I'm pretty sure many of you are excited to see these appear. So that's for REST. So next is, did I mention it's fun? Yes. USB MIDI class driver, Zephyr. You probably know that. You've probably interacted with at least the CDC ACM class for doing UART and consoles over USB, but Zephyr as a USB device stack, right, with the implementation of things like mass storage and USB over IP and a bunch of others. Those standard USB classes. And one new addition, waiting for USB video, which I think will be for the next release. But this time in this release, we landed support for USB MIDI. MIDI as in, yes, the multi-decade-old standard for music interfaces, which has sort of a USB flavor / variant. And so what that effectively means, and this is a contribution from someone by the name of Titouan, was like, it's almost the first contribution of the gentleman, and it's awesome. Like, it's like, I don't know, thousands of lines of code and code sample that comes with it, code sample that just works. Like, take this code right here, as long as your board has a USB a device interface, some kind of button, then just flash it to your board, connect the board to your laptop over USB, and use either, I don't know, like if you're on the Mac, maybe you have GarageBand, or I don't know, I'm not a musician myself, but you may use a tool such as GarageBand, or you can actually use There's like web interfaces, websites that can use web USB to chat with you're now a Zephyr powered USB instrument. And then, yeah, just start pressing the button and you will be doing music. And so one thing that I want to show, which basically based off of this code sample, which, I mean, we can briefly look at the code because it's interesting to see how little there is for someone building on top of this new USB MIDI driver slash subsystem. There's a subsystem provides to effectively create a note, like a command, a MIDI command that's going to be sent over USB to the host, and that's it. And it's actually both ways. It's either like you can think of your Zephyr device as the instrument that sends note or commands to something that's going to play audio and play music, a synthesizer, or can also be the other way around. You can have your Zephyr-based MIDI thingy listen to notes slash commands coming from someplace else, and maybe it's going to be your Zephyr device who's going to be actually playing the music or synthesizing sound or giving you some kind of visual cue as to what is the music traffic on your MIDI wires. So yeah, long story short, this sample is just great because it works out of the box. And when you start adding to it with so that this board right here, it is an Adafruit macro pad. So it's actually a really nice device. Support for it was added in this release. It's based on a Raspberry Pi Pico, and it has a bunch of things, keys, RGB LEDs, a rotary encoder, USB interface, a few other things, and all of that just works out of the box in Zephyr. Did I mention the LCD? I'm not sure, actually. It has an LCD display, which means that you can leverage many of the things that are pre-integrated in Zephyr. Back to my point earlier about Zephyr being more than just an RTOS. Zephyr has pre-integration with LVGL for building graphical user interfaces. Zephyr has an input subsystem that makes it really easy to tap into, say, rotary encoders and get data out of them in the form of actual input events like wheel rotates left, wheel rotates right, sort of stuff. Zephyr has RGB LED drivers. What else? Probably a few other things that I forget, but essentially all of those are put in action and work in tandem in this particular demo, where I built on T21's demo to add more to it, to add like visual feedback. There's a menu that you can use to configure basically how your instrument behaves. Like you want the keys to play according to various scales. You want to apply reverb. What's the volume? Like what's basically the intensity of the notes that you're going to hit? What's the bass octave, etc. Octave. And then on my laptop, I've connected the device and I'm saying, yeah, apologies if it's blurry. I mean, you can see the bass that's being drawn. So you probably understand that what's going to happen is that when I start playing my instrument, it's going to be playing bass sounds, right? So let's move the mic closer to the laptop and let's do some music. How cool is that? I call it the Zephyr song. I just wrote it, improvised it, right? But yeah, no, that's really, really cool. I mean, the MIDI stuff I think is really, really cool. I think what's also cool, as you saw in the demo, is that it's just one of those things that just integrate nicely with everything that already exists in Zephyr. Like you want to use like whatever couple of lines of code are needed to enable USB device support and USB MIDI support. Yeah, like literally just a bunch of kconfigs, right? Like I want to enable like literally a couple of kconfigs. I need USB device stack. I need USB MIDI, the input device to handle the buttons. In my case, I added support for, I pulled in LVGL. I pulled in drivers and support for RGB LEDs, and I was in business, right? So that's I really encourage people to have a look. In fact, it's already like it's barely been released, and yet you will find on LinkedIn and on social media there are people who build already crazy instruments like guitar pedals and whatever using this. So my silly experiment right here. There's many other people doing just the same, which is really cool. And like I mentioned, stay tuned. No pun intended. Stay tuned for USB video support, which I'm pretty hopeful will be landing in the next release cycle. So come July of this year, we will very, very likely get support for USB video. So think basically in addition or similar to how you can build music instruments with Zephyr, you will be able to build webcams and any other video-powered devices. So couple more things. New boards. Don't think I prepared any demos because I would have been running the Hello World potentially again. But the Raspberry Pi Pico 2 is now supported in Zephyr. It took a lot of work, and many community members were, as you can imagine, passionate about bringing support for Pico 2 in Zephyr in addition to the existing Pico. So it's now a thing. I realized we sort of forgot to mention or call that out here, but also interesting to note that the Pico W is supported. So like the Wi-Fi chip that makes the Pico effectively a wireless / Wi-Fi device. This is now supported as of December of this year. So pretty cool. WCH CH32 blah blah blah. This one you may have seen. I think it's a fairly recent chip, but when it initially came out, it made the rounds because it's a really, really tiny RISC-V based MCU that happens to cost like 10 cents of a dollar or something like that. So really, really cheap and actually a good platform for learning Zephyr, I would say, because it's it's like pretty thin piece of hardware with like only a couple kilobytes of RAM. Pretty limited in many ways, but it's sometimes that's what you want, right? And it's cheap, so that's pretty cool. Also worth noting, I don't know if it's at least a half a dozen new boards that were supported that are like specifically boards with both CAN and USB device capabilities. And the context here is that people from the connectivity open source project spent some time and effort into making this a reality. Because basically what connectivity is a stack, an open source firmware based on Zephyr to build USB to CAN adapters, transceivers, whatever is the right term. And so, yeah, like whatever board off of AliExpress or anywhere else, really like pick the one you like the most, and it will just work now. So it's pretty interesting. Those dozens of other boards. You can have the full list here, but just quickly scrolling through the list, you can see that major silicon vendors like Analog, and I think we will see probably Silicon Labs further down the list, right? Renesas, definitely, Scilabs, and many others. They have a lot coming up, and that's compatible with Zephyr, and that's or sometimes even like targeting Zephyr as their main sort of BSP and main target. So it's really nice to see. Some of the CAN stuff you can see here. So yeah, check out the list. There might be and just lots of stuff from ST also, obviously. So there's that. And last but not least, let's scroll down to the very bottom of the list. What do we have here? Other notable changes. Actually, I need to refresh the page. Yeah, there we go. Interesting. This one we just pushed. So check out the full list. Like the HTTP server keeps getting improvements. A few things that I wanted to call out right here. This guy or this bullet point is about something that is very much like to some extent, an internal detail of how the Zephyr has refactored the way devices and device driver APIs are managed, but it effectively has impacts for anyone and for all the end users. And of course, it has an impact for people who write device drivers, but essentially, the driver APIs and driver API structures are now put in iterable sections, which basically make it possible for the Zephyr kernel to know at runtime, given a particular device struct, figuring out whether it corresponds to, say, a sensor or a UART or a GPIO or GPIO controller rather. And the idea with that is that anyone writing code manipulating devices may now use the device API is macro to get a sense of what like whether a particular device is of a given class, which means that if you run shell commands that would typically expect and give you auto-completion of with and give you a list of devices to choose from, now it's much smarter, right? And so I should have a demo, I believe, right here. Let's see. So let's switch back to main Zephyr. All right, and so the sample I want to show you is basically where am I? Just a quick West update for sanity check, and yeah, I think I have sensor. Yeah, this guy right here. So just building a sample running on, again, a QEMU emulated target, but effectively running the sensor shell sample on a board with an emulated sensor. And so sensor command, the main sensor command accepts a bunch of subcommands, one of which being getting sensor data out of a particular sensor. And in this case, when I try and get the list of what I can pick from, it only gives me actual sensors, right? As opposed to in the past, it would have basically it wouldn't have known what kind of device I expected, and so unless people used other tricks, it would have just given me the full list of all UARTs, all sensors, all GPIO controllers, all I2C controllers, blah blah blah. So it's actually making a huge difference in making you more productive, right? When you use the shell, with which I think I've said that pretty much every video since I started doing those. If you don't use the shell, please do, because it's awesome and saves you a lot of time. Last but not least, the Zephyr board catalog. You remember that, right? From I think it landed in 4.0. It was an addition back then, giving you the ability right from the board index out of the 692 at the time of recording and at the time 4.1 goes out, gives you a list to give you a way, to find the board that you're looking for. Either you know the name already, or you know kind of like roughly the name, and you find the board you need, or you don't know yet, but you have a sense that you want to go for an expressive C6. Well, obviously C6 wouldn't be ARM. What else did I? do wrong right here? Let's just reset the filter. C6. Yeah, there's two options right now in tree to choose from. So that's one way to sort of play with it. What are all the boards that support XYZ? What are all the boards from a given vendor, etc., etc. But something new is the ability to search by supported hardware capabilities. So the UI there will likely be improved over time. But right now, basically, and you can see the list, the auto-completion right here. Think about like the keyword of whichever capability you're interested in. Just type it in. You'll get autocomplete anyways. And in my case, I would like to get a board that has, I want to do some LoRa stuff. And typically LoRa, it's for some kind of like IoT scenario. I want a board that already has some sensors on it. And of course, you could be adding more, right? Like a board that has, actually, I didn't try beforehand, but maybe, yeah, I want crypto as well. So that's the one I want to pick. I want this guy. I have it in my drawer actually. So I'm glad I get the confirmation that it's one of the boards that I can use with Zephyr. One of the boards that I can use to do LoRa plus sensor plus crypto stuff. And what's more is that we've added something kind of like based on the same infrastructure that powers the search engine. There is also now a list that's de facto correct, as opposed to something that was usually manually maintained, a list of the supported hardware capabilities of the board, like whatever peripherals the board has and for which a Zephyr driver exists, it shows up. And we kind of get the confirmation that the board indeed does LoRa. It apparently has a GNSS modem as well. I had no idea. It looks actually like a really, really neat board. It has integrated EEPROM. How about the crypto? I asked for crypto, right? So yeah, apparently crypto is through the Nordic chip, because I guess it's an NRF, yeah, 52 something. So it does have crypto acceleration capabilities, either ECB or AES, AES, CCB or CCM. And sensor-wise, apparently, it has quite a few. It has a pressure sensor, air quality sensor, etc. Sorry, I should have, I clicked inadvertently. So yeah, that's what I want. So I can now like go for this board. And something else that it also allows you to do really easily is for each of those sort of like peripherals that are enabled in the board, you can really quickly navigate back to the device tree, which in many ways is, I hope, is something that will help people familiarize themselves more and better with what device tree even means in the first place, and or easily get some inspiration, like rather than grepping and searching in their source tree to figure out how to use device binding XYZ, you can actually that's another way to find your way around. So there's that. That's yeah, and we keep improving the documentation. We do our best to improve from one iteration to the other. If you have, of course, feedback, either documentation wise or on anything else we covered here, really, I think you know where to find us. Typically, the community hangs out on Discord. So chat.zephyrproject.org. It's probably a good starting point. Of course, GitHub. Engage on GitHub issues. If you stumble upon any bugs, GitHub discussions to chat about technical topics. Pull requests if you have anything you want to contribute. And with that, we will be back, I guess, in 4 months time, sometime mid-July, I think, is the roughly the next release. And in a couple of weeks, we will be doing a special episode of Zephyr Tech Talks, like we always do, kind of like an Ask Me Anything, where people like Robin, David, Titouan, like the folks basically behind some of the features I just covered today here in this video will be here. Happy to answer your questions. And yeah, don't forget to subscribe to the YouTube channel, because videos like this one or tech talks or anything really, you don't want to miss them. So make sure to subscribe, and I'll see you when I'll see you.